our project is designing a scalable robotic exoskeleton and tablet gaming suite for hand function rehabilitation. My name is Kristen Fernandez. My team members are Jennifer Hunter and Jonathan Tuck. Our graduate mentor is Brittany English, and our faculty advisor is Dr. Ayana Howard. So, as an overview for our project, stroke survivors, as a result of a stroke, often have a motor impairment, and due to this, they're rated as poor participators in physical therapy. So if a patient cannot complete their physical therapy, this means that they have a drastically increased recovery time and they can't improve their motor function. So this can have a really negative impact on overall health, including both physical health and mental health. So if you have a motor impairment, then you can't really take care of yourself, you can't do a lot of daily and simple tasks, you need to rely on other people to help you. And this just really strips away your independence and your privacy, and it can really lead to depression. So studies have shown that elderly people with depression have a shorter lifespan than elderly people without depression. So having a motor impairment can really just have a really negative impact on perceived quality of life. So to solve this, our team proposes that we use the minnow board on a scalable exoskeleton that will go on the patient's wrist and hand to capture and convert their hand motions and use them as inputs for therapeutic video games. So if we have patients playing these therapeutic video games, if we gamify the therapy process, then this should make physical therapy much more fun and engaging for the patients. In the short term, by playing these video games, the patient will have fun, they'll be enjoying themselves, they'll receive a lot of encouragement and positive feedback from the video games, and in the long run, since the patients are actually doing their exercises through these video games, they'll be improving their recovery time. This will have a really overall positive impact on their health because they're improving their motor function, and so they can take care of themselves now, they can have their independence and their privacy back, and this should really have an overall positive impact on their perceived quality of life. So as an overview on how we're going to use the Intel Atom, last year our team used a different microcontroller, and we used different sensors and electronics to read the inputs from the exoskeleton, and we used that for our video games last year. So this year, our team is going to use the Intel Atom Minnow board, and we're going to read in the inputs from that and send them to our tablet using a Bluetooth connection. So we're also going to be using an Intel Atom powered tablet, and this tablet will contain all of the rehabilitative games that our team is going to create. So before we go into more technical details, I'd just like to highlight some of the features for our product. So the overall goal for our team is to create an easy-to-use, rehabilitative product that will increase a patient's quality of life. So by using our product and going through the therapy process successfully, this is directly related to the patient's overall health. So like I said before, if the patient can successfully go through therapy, improve their motor function, this will increase their health, like both their mental and their physical health. They can have their independence and their privacy back, and overall increase their perceived quality of life. So the cost of producing our device is relatively cheap for a medical device. It's only about $150. And our product also has a scalable design. So we can target anyone from a small child to a large adult. So this really increases our market size. So some background for our project. There's a lot of debilitating neurological disorders, such as cerebral palsy or stroke, that can really damage or impair a person's body movements or their muscle coordination. So as you saw from the picture of our device before and from the picture on the left over here, where our team is going to be focusing on hand and wrist motor function. And that's because having hand function is the number one factor for a person's perceived quality of life. And this is because if you have fine motor control in your hand, then you could do a lot of small daily tasks that really give you your independence and allows you to take care of yourself properly. So let's say we have a patient here who has some reduced motor control in his hand. And in order to regain or retain some more motor function, he will go through the physical therapy process. And by going through this process, he will hopefully improve his motor function and have an increased quality of life. So the way that the physical therapy process works is that once a week, the patient will go and see his therapist, and will do an hour-long session with his therapist and do exercises, like therapeutic exercises with his therapist. And then the other 6 days of the week, the patient will be at home and doing these hour-long sessions every day, doing these sessions by himself. So the problem with this is that when the patient is doing these exercises at home by himself, he's often in pain or he's bored. And if this happens, then he's less likely to actually do his exercises, and this leads to a longer recovery time, as you can see in the picture here. However, if the patient can stay engaged during their exercises, if they're having fun, if they're enjoying themselves, then they'll actually do their exercises, and this will lead to a shorter recovery time. So studies have shown that robotic exoskeleton therapy is an effective way to keep patients engaged during therapy. But the problem with this is that children and women, who are the groups that are the most affected by cerebral palsy and stroke respectively, don't really benefit from this kind of therapy, because current systems for robotic exoskeleton therapy are targeted towards the average adult male. So a lot of groups can't, or so current systems cannot fit a lot of groups such as women and children.
So to combat the three problems that Kristen just mentioned, last year we developed a robotic arm exoskeleton for use in wrist rehabilitation therapy. We developed the robotic arm exoskeleton using computer-aided design, primarily SolidWorks. And after developing the exoskeleton in SolidWorks, we then printed the exoskeleton via 3D printing, which is not only fast and easily prototypable, but it's also inexpensive and easily scalable for pretty much any size. And after printing and assembling the robotic arm exoskeleton, we embedded electronics on the exoskeleton, such as a microcontroller and a potentiometer, so that we can map the movement of a wrist to a voltage. And by mapping to a voltage, we're then able to use the wrist movement as a video game controller, which is exactly what we did. We developed a video game similar to Guitar Hero, where the notes move across the screen, and the patient can hit the notes with a guitar pick, controlled by the wrist movement. And so this year, we're looking to expand our list of application spaces. Like I said, last year we worked on wrist rehabilitation, and this year we're focusing on grip strength. Now, the reason why we're focusing on grip strength is the most important factor in the perceived quality of life for a patient, as it gives the patient the most independence. Grip strength is immensely important for tasks such as feeding oneself, dressing oneself, and even toileting oneself. And research shows that completing these independent tasks like this contribute to a heightened perceived quality of life. We are using an existing grip strengthening device, as shown to the right, the Grip Master, as our base for the controller. And in designing this controller, the Grip Master is going to be embedded with 4 sensitive resistors. So each button on the 4-button Grip Master will be able to map the pressure put into it by the patient's finger to a voltage, which, like last year's experiment, will be able to then map to a video game control. And so using pressure-sensitive grips gives us electronic feedback in terms of performance metrics of the patient. And in addition, the Grip Master, because it's built with spring-loaded buttons, it encourages the patient to complete their grip strength exercises. We developed a small device in SolidWorks to attach onto the Grip Master and connect the Grip Master to our existing robotic arm exoskeleton. This is incredibly important to us. It is important that our patients can seamlessly switch between wrist rehabilitation therapy and grip strength rehabilitation therapy.
So from a software perspective, we're switching from using the Android-based Android Studio to using the Unity game engine. What this allows us to do is actually develop for both Android and iOS. It also has other really great benefits, such as improving the game quality by allowing us to use pre-made models, and also drastically improves the amount of time it takes for us to develop games. So for this year's research, we're focusing on creating a variety of simple mini-games that are completed using that therapeutic motion of moving the wrist from complete palmar flexion, dorsal flexion, or from all the way up to all the way down. And after talking to some physical therapists after last year's research, we discovered how important it is to also include cognitive tasks, because specifically for patients recovering from stroke, one of the common symptoms is multitasking disorder. and it becomes a big part of their therapy. So we wanted to make sure to include multitasking in our games. You can see some examples of this in the screenshots on the right-hand side of the screen with the colored box and the math equation. And we'll go more into detail during our demo video later. Lastly, one of the big features we want to focus on this year for software is increasing engagement through multiplayer or group play. And so this, we're hoping, will be a similar system to having a fitness buddy you go to the gym with, or even having a study buddy that you'll do classwork with. And what we're doing is trying to increase that motivation and almost introducing competitiveness into the gameplay to encourage people to stay with the games and stay with their physical therapy exercises. So here's our current layout for how we're planning to complete the software side. We're currently in phase 1, which is developing the mini games. And what this includes is translating data from the robotic exoskeleton into clear gameplay. So that can be moving a character around or rolling dice. And this will help us transition into phase 2, and that's completing a virtual board game. So we're hoping for a design similar to Mario Party, which, if you aren't familiar with Mario Party, it's essentially you have characters on a virtual board, and what you do is you roll dice and you move a certain amount of spots, and that spot can either give you points, it could take away points, or it could trigger a mini game. So this is where we want it to come in, and with phase 3, integrate the mini games into the virtual board game. This will also be the area in which we'll start integrating the multiplayer gameplay for the mini games within the overall virtual board game. Our current status right now with our progress is that the wrist exoskeleton is completed. As described by Jonathan, our finger exoskeleton is in progress, and our exoskeleton scaling software for physicians to use to apply the exoskeleton for different people is also in progress. Minigame 1 and 2 are completed or very close to completion, and minigame 3 and 4 are in progress. Finally, our system validation and results are currently in progress. Now we'll be moving to a short demo video of our product. So here you can see one of our games from last year called Jet Boy. Essentially, you have a little spaceship on the left side that you can control with the robotic exoskeleton. So as you can see, one of our participants has the robotic exoskeleton on, and you can see her move her wrist. And it's a little hard to see, but you can see that there's a figure on the left-hand side of the screen that's moving up and down in response to her wrist movements. What I really want to stress here is the wrist motion and the interface between the game and the exoskeleton. Now, this is a completely wireless and Bluetooth interface, so you can stand a few feet away from the tablet or as close to the tablet as you want. Now we're going to switch focus to the games. Right here is one of our first games that's close to completion. The objective of this game is to catch the fruit. And the therapeutic motion here is moving the turtle character back and forth by using the exoskeleton arm. And the cognitive task is the colored box you see in the lower right-hand corner. Now the goal of this is to catch the fruit matching the colored box. So if, for instance, you see it's yellow, that means you'll only get points for catching bananas. So while you can catch other fruit, and for instance it's purple now, you'll only get the points for the grapes. And once a fruit hits the ground, it's out of gameplay. One of the things I really want to stress here also is the timer and the point system. One thing we try to really focus on in our games is only providing positive points. And so you can't lose the game, you can only try to improve. And so we're hoping this really helps participants focus and just kind of improves their morale. And one of the cool Unity features was the spawn points that brought the fruit down. So now we'll be transitioning to a game, our second almost completed game.
So in this next game, you'll see that there's a simple arithmetic equation on the screen. 1 times 1 equals question mark. And your goal is to move the ship back and forth using your hand motions and collect the star that has the correct answer that answers the equation. So you'll notice that you only get points for collecting the correct answer. So as Jenny said before, we only want to provide positive feedback for our users. So you get 10 points for every right answer, and you don't lose any points for a wrong answer. And then every time you get 30 points, the equation on the screen will change. So this game also facilitates that multitasking that Jenny was talking about before by combining both a cognitive task with a motor task. So the cognitive task is actually answering the equation and then identifying the star that has the correct answer. And then the motor task is moving your hand back and forth to control the ship. So you'll notice in the lower right corner, there's a timer that's started at 60 seconds, and once hit 0, the game is over. So for this next game, well, as Jonathan said earlier, we're going to be focusing on grip strength. So you'll see there that's our exoskeleton with the grip strength device. And we're going to be using the buttons on the grip strength device as inputs to our next game, where each button will correspond with a number between 0 and 4. So you'll see a series of numbers show up on the screen, and then your goal is to memorize the series of numbers and then hit the correct button on the device in the correct order before the timer runs out. So those white squares on the screen will turn either green or red depending on whether or not you got the answer correct. So in that past round, the user got all of the answers correct, so all of the squares turn green. Like the other two mini games, we also want positive feedback, so you get 10 points for every right answer, and you don't lose points for a wrong answer. And you probably notice that as each round goes on, the length of the sequence gets longer by one number. So we're gradually increasing the difficulty of the game by having you memorize more answers in the same period of time. So this game is still in progress. So I'd like to work on some of the background and the animations for the character. So instead of having him just stand there idly in the middle, possibly have him do some sort of dance or another animation whenever the user gets a correct answer. So the next video game will be coming up now.
Okay, so our next video game here is our second in-progress video game, and the objective is to complete the pattern described on the bottom and find a gem that's hidden in the correct hallway. So for instance, the pattern here is green, green, red, red, blue, blank. So the logical answer to that would be blue, but the first hallway we chose was red. And then next, for demo purposes, we're going to go down the green hallway. Now the therapeutic motion here is moving the character using your wrist, and the cognitive action is choosing the correct hallway. And so the overall goal is to collect as many diamonds as you can in the time period by traversing the correct hallways. So what this means is when you go down a hallway that's correct, you'll find a diamond, but if you don't go down the correct hallway, you still have a chance to find that same diamond. And we'll be implementing that when you hit and collect the actual diamond, you'll be reset to the beginning with a new pattern to complete. Okay, now we'll be moving on to the results of our research so far. So far, preliminary results and validation have included engagement and testing of the actual exoskeleton. For the engagement validation test, we gave 14 participants 2 tasks and allowed them to choose which task to complete first. The first task was using the exoskeleton to play a game, and the participants were told to play the game until they felt bored. The second task was just the exoskeleton, and participants were told to exercise until they felt bored. Participants played the game on average 4 times longer compared to when they just exercised. Now for validation of the exoskeleton, we gave a single participant, told them to alternate between palmar flexion, dorsal flexion, or having your wrist all the way up to all the way down at a comfortable speed for 5 minutes with their arms suspended in the air. Our test cases here were the Hand Mentor, which is the commercial model for the robotic exoskeleton, versus our prototype, here labeled HM and P in the graphs on the bottom of the screen. We also tested with both participants' dominant and non-dominant hands. So in this case, the participant was dominant with their right hand. And here we're really looking at counting the number of exercises and the amount of time spent resting with the device. And as you can see on the screens below, as far as exercise motions are concerned, the participant was able to complete significantly more exercises with our prototype, and they spent a significantly reduced amount of time resting. And in the case with the participant's dominant hand, they actually spent 0 time resting, which shows to us that the exoskeleton can help increase the productivity of the participants' physical therapy. It also shows us that our weight can be a really big factor in this, considering that our prototype is about 10 times lighter than the commercial model. For future validation, we want to do a validation test with elderly adults, particularly addressing a problem that elderly adults face with physical therapy in that they forget what exercises to do or how to complete the exercises. So similar to our preliminary engagement validation test, we decided to we're going to put elderly adults into a situation of playing games with and without the tablet game. And first, really analyzing their motions versus visual cues. So they would be training with a physician first, and then exercising by themselves versus exercising with the game. Our second validation that we're looking to do is studying cueing methods, so specifically visual versus musical cues, and analyzing whether music helps participants learn the tasks faster, and looking to see if we can improve participants' reaction time and fit them closer to the ideal motion paths.
So now that Chris and Jenny have talked about our successes, I'm going to talk a little bit more about some challenges in completing this project and how we persevered through them. So first, let me explain what our original idea was for the end game of our project. A clinician would be able to take a few parameters from a patient, such as arm length and wrist width, and then input those to a program which will be able to output a few printable files to be printed and assembled. Unfortunately, building the software turned out to be more of a problem than expected. So for this software to work, after developing a MATLAB executable file, it would have to open up SolidWorks, change the parameters, close SolidWorks, and output the file. Unfortunately, SolidWorks wasn't too compatible with this idea, and so we opted for another route. The process of scaling is highly nonlinear, but it just so happens that for human arm sizes, scaling is fairly linear. So we simply use linear scale factors, which can easily be applied to a base file to get different sizes immediately. Our second challenge was that our original games were built in the Android Studio, but we switched to Unity to do the 3D video games. So in doing so, our Bluetooth code was incompatible for our new video games. So we mitigated this challenge by purchasing existing Bluetooth code for only $20, which is a fixed cost that allowed us to allocate important time to completing the video games themselves. And so now, as for the cost of the project, looking at the supplies to create this project, assuming bulk prices, it costs only about $1 worth of plastic, about $50 of electronics, which basically includes Bluetooth device, sensors, and a potentiometer, a $99 motherboard, of course, and then the cost of a tablet or smartphone is approximately $500. But considering that most people nowadays have either a smartphone or a tablet, the cost is not really in the spectrum of our supplies, really. Now, as for the time to create this robotic arm exoskeleton, compared to commercially available robotic arm exoskeletons, which can take days to weeks to bring to you, the time it takes to build a robotic arm exoskeleton is about 8.5 hours. It's about an hour of a clinician's time to measure the patient, about 7 hours of powering a 3D printer to print the 3D robotic arm exoskeleton, and about half an hour to assemble. So you could create, if you started creating a robotic arm exoskeleton at the beginning of a day, you could have it by the end of business. And so, as for our software expenditures, we had two fixed cost, very low price software expenditures. First was, like I said before in our challenges, we used $20 to allocate to Bluetooth code, and then we also paid $35 for a small character pack for our video games. Now, as for our future work, we want to complete minigames 3 and 4 that Chris and Jenny mentioned. We want to create the board game interface for the Mario type party game, for the Mario Party type game. We want to integrate these mini games with the board game itself, and then we want to move into, on the hardware side, a new area of application space, which is finger exoskeleton rehabilitation therapy. And by integrating the final game with our finger exoskeleton rehabilitation therapy, we will finally have this robotic arm exoskeleton therapy suite, where we have a multitude of video games with a multitude of exercises. So in conclusion, stroke survivors are poor participators in physical therapy, which leads to increased recovery times, as we know. And so By using a robotic arm exoskeleton to convert the movement of a wrist or the grips or the pressure of a grip strength device to video game inputs, we can actually create a video game out of physical therapy. And so that's really the crux of our project. We want to make gaming, we want to make therapy more fun, and we want to turn it into a video game so that we can reduce the recovery times and increase the perceived quality of life in these patients. So now we open the floor to questions.